then you're ready to go.
How is the position of the inner plate defined?
So these bays are exactly for that. Therefore, constrain the position to match it as better as possible with our digital model. So, yeah, yeah. So there is a whole system of rules. So the cassettes have a mark, and the workers who are loading the elements all the time, they are following our instructions or this kind of agreement that we have with them. There is marks. So the longest edge always goes into the big wall, and there is a mark that should be on this corner, and then there is no ambiguity on how the place should be placed, right? The same for the beams. There is a notch that you can only see from that side, a little rounded notch that you can see later, and then there is this plain stopping back there, and the last part of the beam catches and thing, and then the position is matching as best as possible with our digital model. Of course, there is tolerances, right? So we accounted for 10 millimeter tolerances because in this type of system, this part as it's developed right now cannot have this zero tolerances in which the elements are actually connected, right? Because the only thing that matters is the structural criteria. So it's the same if they are 1 millimeter apart or 1 centimeter apart structural wise. Because we're not connecting them like laterally, they're only connected to the plate. So the plate transfers the force actually from the plate to the beam and the beam to the So that was the first part of the process. You put the plate, you put the glue, and then this robot will place beam by beam. So the robot has these rows more or less. This robot is in charge of what we call pick and place. It has both a pneumatic gripper, which is what you can see right now for the beam. These two vacuum grippers are for like lifting the plate. Or sometimes when we have bigger beams, we can also use one of the grippers to grab it. The other robot is called GNN, which is gluing and milling. Of course, milling is like this second part of the process I was talking about that happens later. So ideally, we glue all the cassettes together and then we move them all together. Of course, like sometimes in the whole process we're switching between gluing and milling, because of logistics of the fabrication of the assembly side. But it's really separated. You can glue all of them, finish, and then just mill all of them. In relation to how to match the coordinates and that, of course, like every single part of the process will add some tolerance. So first is to be able to match the robot on the same space, which is quite tricky actually. Even before that, you need to match. There's a third element that I haven't mentioned, is the turning table, right? The turning table strictly belongs to one of the robots, so that relationship is down to a millimeter, less than a millimeter tolerance. But within the robots, it depends where you are on the cell, the tolerances vary, right? Because that calibration is quite tricky. So in the end, I think we got it to. Between the robots themselves, there is around a millimeter, 1-2 millimeter tolerance. But every part of the process, like kind of adds noise, about the tolerance. So either the beam placing, the beam picking up, the plate placing, and everything. Luckily, for the process, it's taught. So once this is milled, only the tolerances of the milling will affect the final geometry, right? Because you need to have actually almost zero tolerances in one of the faces of the single joints and 0.2 millimeters on the other direction. I can explain this later a bit more when we go see the elements, right? But the frontal face of the finger joints, I meant to have almost zero tolerances, and the lateral faces is what gives you some space for putting them together. You will see that when we're trying to assemble the spines later. Yeah.
Why is the last
Yeah.